Okay, so this is the outline of chapter 29. So first of all, we will introduce the magnetic field due to a current. Okay, so which is the easiest case. Okay, and then we will talk about the force between two parallel currents. So in the last part of the last chapter, we talk about when we have a wire, if we have a current in the B field. Okay, so here we will talk about when we have a current, it will generate magnetic field. So if we have two parallel current, one of the current will generate a B field, and then this B field will influence the other, and vice versa. Okay, so if we have two parallel current in the same direction or in opposite direction, there will be force acting on the parallel current. And then next we will talk about the Ampere's law. So this is the second law in the Maxwell equation we learned. Okay, so for the first one it is called the Gauss law, and then the second one Ampere's law. In the next chapter we will also learn the Faraday's law. In chapter 32 we will learn about the Gauss law for the magnetic version. Okay, so and then we will talk about the solenoid and toroid, and then we will talk about the current coil as a magnetic dipole. Okay, so this is an overview of the electromagnetic sum, just as what I've shown you in chapter 23. Okay, so when we talk about electromagnetic sum, so in the simplest case, we can just mention it in two words, Maxwell equation. Inside the under the Maxwell equation, we have four laws. Okay, first one is Gauss law. We learned it in chapter 23. And for the Ampere's law, we'll learn it in this chapter. Although the notation are not the same. Okay, so in this equation, you see the Gauss law is use d dot ds. Okay, of course in our textbook or on the slides, we write it as a epsilon naught integration of E dot dA. Yeah, and then equals Q enclosed. Q enclosed is like the charge density with a triple integral for the volume. Okay, so yeah, but it just will write it like that. Okay, so of course in this chapter for the Ampere's law, we only learn up to this part. We don't have this part yet. In chapter 32, it will come back. It will come back. But yeah, for some of the textbook, it just mentioned the whole is the Ampere's law. Even when I learned physics, I just learned the whole thing is Ampere's law. But in this textbook, it called Ampere's law to be up to the first term. And for the second term, including the whole thing, it called it Ampere-Maxwell's law. Okay, but anyway, it's just a name, it doesn't really matter. And then for the Faraday's law, okay. But anyway, in this textbook, we will still use another notation like integration of B dot and ds equals I enclosed, something like that, to make it easier. Okay. Of course, we will also mention about the point form or the differential form in chapter 32, but we will learn it later. Okay, so here we mentioned the magnetic field due to a current. Okay, so you can see the magnitude of the field dB. dB is a small B field generated by this small segment. Okay, so you can see we have a current, we have a wire with a current I from bottom to top. Okay, it is not a straight wire, so we need to cut it into many small pieces. So this one is ds. ds will generate B field in the whole space, but here we only consider the point P here. So for every segment, it will generate dB on this point P. Okay, if we want to find the total B field generated at point P, then we need to find the dB for every segment, and then we add them together as an integral. You can imagine. Okay, so the idea is like that. So we have dB. D is just the delta. Okay, not a variable. So dB. okay, equals mu naught over 4 pi. Okay, so up till now we have not introduced mu naught yet. Okay, here we come the mu naught over 4 pi, and then I times ds. ds is actually this small segment, and then sine of theta. Okay, so here we can see sine of theta, so you can imagine there should be some cross product, and then over r square. Okay, so here first of all we would like to introduce mu zero is a constant called the permeability constant, whose value is defined to be exactly 4 pi times 10 to negative 7. 4 pi times 10 to negative 7. Okay, so it is, yeah, the pair between the duality for the epsilon naught in the for the E field. So for the epsilon naught, it is called permittivity constant. This mu naught is called permeability constant. Okay, so we have epsilon naught and mu naught. Okay, so comparing with the Coulomb's force, the Coulomb's force is like F equals 1 over 4 pi epsilon naught times Q1 Q2 over R squared. So you can see they look somehow alike. Okay, we have 1 over 4 pi. We have epsilon naught in the denominator. We have mu naught in the numerator. We have something multiplied together. Okay, but of course this is just a simple multiplication. This will look like a cross product. We also have R squared here. Okay, so yeah, so it is somehow like that. And yeah, so one point to note is that for the epsilon naught in the in the formula for the E field, we sometimes see epsilon naught, or sometimes we often see 1 over 4 pi epsilon naught to be a K. Okay, when you see this epsilon naught for the E field, some formula for the B field will be like, would you change epsilon naught to 1 over mu naught? Okay, so that's why this mu naught go to the top. And just as what I mentioned in the last hour, UE is like 1/2 epsilon naught E squared. And then if you change to the energy density for the B field, it becomes change E to B, and then 2 to be the same, and then epsilon naught to be 1 over mu naught, so it go to the bottom. Okay, it is always like that. So it's just like the duality. Okay, so yeah, so for this epsilon naught and mu naught, we have an important value called 1 over square root of epsilon naught mu naught. Okay, this is actually the speed of light c. We will actually learn it in chapter 33, actually the last chapter in this semester. So this is the speed of light. Okay, speed of light. Okay, so yeah, and that's why the light is a kind of an electromagnetic wave. 光是电磁波. Okay, so it's related to the electric field and the magnetic field. Okay, so if we just write this equation in a vector form, it will be like dB to be dB vector, and then mu naught over 4 pi, this is just a scalar, so nothing special. I is also a scalar, so nothing special. R squared, just keep it there. Okay, so finally, ds sine of theta, it should be a cross product, but nothing cross with him. So we just introduce a R hat. R hat is the unit vector. Is the unit vector of R axis. So what is R axis? Okay, so this term become ds vector cross with R hat. Okay, so let's see. On this vector, this is ds, and then the current points to this direction. So ds is pointing to top left, okay, and then I is a positive value, so ids also points to this direction. And okay, so here ds is a small segment, so you can consider it as a dot. Okay, then you can connect this dot with the point you concern. This point P is what you concern for the B field. Okay, so you try to connect this point to this point. So our axis is in this direction. Our axis is in this direction. Okay, if you consider a point P prime, okay, so the R axis is in this direction. Okay, so our head is actually our head points to this direction and with unit length. Okay, so this is our head. Then we can see that in this equation we have ds cross our head. Okay, so ds points to that direction, r points to that direction, so b is actually pointing into the page. So we can see that db is pointing into the page. Okay, so actually this one we actually call it the law of Biot-Savart, or Biot-Savart law. Okay, sometimes the textbook call it Biot-Savart law, and sometimes it call it the law of Biot and Savart. Okay, but anyway, yeah, so actually it's just a law, so we cannot prove it. So we just try to believe it is correct. Just something like the Coulomb's law. Okay, it's also a law. Okay, so here, based on the Biot-Savart law, we can be able to calculate the B field generated by a long straight wire. So here we mentioned for a long straight wire. Okay, so as I mentioned earlier, long means infinitely long. 无限长的 infinitely long. Okay, long straight wire, 直的 wire carrying a current I. The Biot-Savart law gives for the magnitude of the magnetic field at perpendicular distance out from the wire to be this one. Okay, we can actually derive this one using the Biot-Savart law in the next page. Okay, likewise for semi-infinite straight wire, which means that it starts from 0 and then goes to the infinity, and then you consider the point P, the B field at the point P. Okay, so this is the wire. Okay, the current can go in this way or that way. Okay, it just changed the direction of the B field without changing the magnitude. Okay, so if it is a semi-infinite, if it is semi-infinite, which means that it starts from 0 to infinity. Okay, start from 0 to infinity. So it's just a half straight wire or semi-infinite straight wire. The magnitude is just half of it. Okay, so very straightforward because yeah, these two are symmetrical to each other, so both of them will contribute half of the B field for this point. Okay, so let's see how we can derive this one using the Biot-Savart law. Okay, so using the Biot-Savart law, okay, so this is actually the yeah, so this is the 0 point. This is the 0 point of the let's see, the s-axis. This is the s-axis. This is the s-axis. Okay, and this will be the okay, the r axis will change dependently. Okay, so let's see. Here, let's write out the Biot-Savart law dB to be mu naught over 4 pi I ds sine of theta over r squared. Okay, so here it means that it is an infinite long straight wire. Okay, from negative infinity go to the infinity. Okay, and as much as it is symmetric. Okay, for example, if this is ds and this is ds, okay, they will contribute the same thing because this is ds, this is ds, this is r. So ds and r, this is ds and r. This theta and this theta, okay, this is the theta between this ds and r. And then for the symmetrical one with the same s, okay, this theta, okay, because this s and this s are the same, this r and this r are the same. Okay, so this angle and this angle are the same. Okay, so this theta, let me say, this is theta pi, this is theta and theta prime adds up to be 180 degree. Okay, and here we can see sine of theta. Sine of theta will be equal to sine of pi minus theta. Okay, so these two cross product will give you the same value. Okay, and then they will point to the same direction because ds cross r pointing into the page, ds cross r also pointing into the page. Okay, so both of them pointing into the page and with the same magnitude. Okay, so this segment and this segment will give you the same value. Okay, so we can just simplify it to 2 times integration from 0 to infinity dB. Rather than originally it is like integration of negative infinity to infinity dB. Okay, as much as it is symmetric, it becomes 2 times half of it. Okay, so let me plug in this one into here. So 2 and 4 will cancel each other. So we can be, we have mu naught I, and then 2 pi. Okay, so we already have mu naught I 2 pi. The only remaining thing is 1 over r here. Okay, so to come up with this capital R is difficult. We take quite a lot of steps. Okay, so this R is actually, this capital R is here. Capital R is the distance of the point P to the wire. Okay, this R is actually, for example, this ds, the R axis point to this way. This is the R axis. Okay, for this point, this is the R axis. For that point, for different ds, R axis point to different direction. Okay, so here, and also theta also related to s. So we cannot put all the thing out and then integration ds from 0 to infinity or become infinity. This is not correct. Okay, so we need to express theta r square in terms of s so that we can do the integration. Okay, so this is r. This is actually the distance from this point to this point. This is r here. Okay, so according to Pythagorean theorem, r is actually square root of s square plus capital R square. So this is s square, this is capital R square. So becomes small r. And of course take the square root of this sum of square. So this is r. Okay, so r square will be s square plus capital R square. And then as I mentioned, sine of theta equals sine of pi minus theta. And sine of pi minus theta is actually this one. Sine is actually capital R over small r. So capital R over small r. Small r is this one. Okay, so here we have sine of theta to be this one, and then r to be this one. So when we plug in this one to here and then this one to here, okay, then r is a constant. So this function will only relate it to s. So we can see here r square is the inside term, and then we also has this one, the square root term. So totally we have this sum of square to the 3 over 2 power, okay, in the denominator. And then in the numerator, we only have capital R. So this function only have s to be a variable, and then R is a constant. So we can be able to integrate this one. So to integrate this one is not that easy, but anyway, we actually need to do some change of variable, like s to be r tangent theta, and then ds to be r secant square theta d theta. Yeah, but actually you can try to practice it yourself, and the final answer will be s over this term to the square root. Okay. Okay, and integrate from 0 to infinity. So if you plug in 0, so this is 0, this is not 0, so this term becomes 0. And if you plug in infinity, okay, this will become 1. This will become 1 if you plug in infinity. Can you see that? If you plug in infinity, if you plug in limit s tends to infinity, and then here we have s over square root of s squared plus r squared. So we divide s on both the denominator and numerator, and inside the square root it should be s squared. So it becomes limit s tends to infinity, and then 1 over square root of 1 plus r over s squared. Okay, so s tends to infinity, this term becomes 0, so it turns out to be a 1. Okay, so here we have, so this term is actually a 1. So finally we get this mu 0I over 2 pi r. Okay, so we will use this one for many times, very frequently throughout. So you can actually remember this one. mu 0I over 2 pi r, mu 0I over 2 pi r. So mu 0 is a constant, 2 pi is also a constant, so which means that the B field generated by long straight wire related to the current. Okay, if the current is larger, the B field is larger, so it makes sense. And if the distance is farther away, then the B field becomes smaller, and then it is inversely proportional. The B field is inversely proportional to the distance. Okay, so it also makes sense. So this is pretty easy to remember. So B equals mu 0I over 2 pi r. Okay, so the next case is B to be mu 0I phi over 4 pi r, a little bit different. Okay, so yeah, so it means that the magnitude of a magnetic field, at the center of a circular arc. Okay, this is a circular arc rather than a straight wire. Okay, of radius capital R and central angle phi. Okay, so this is just an arc, in radian. Carrying current I is this one. Okay, so this is the arc. So we can simply verify it with the Biot-Savart law. Okay, so we have dB equals mu 0 over 4 pi I ds sine of theta r squared. Okay, so B is integration of dB from 0 to phi, So this is far as 0 to phi. Okay, so we're integrating in this direction. Okay, so here we would like to calculate the B field at the center only. At other point, we don't have a elegant expression. So we only consider the B field at the center of the arc. Okay, so consider ds here. Okay, ds point to top right, and then our axis is from this point pointing to the center. Okay, so this is our, it's actually the radius of the arc. Okay, so we should have ds cross our head, ds cross our head should be pointing out of the page, so we can see the B field is pointing out of the page. And also you can try to use the right hand rule in another way. So you use your forefinger, follow the direction of the current. The current is going like this. You use your forefinger following the direction of the current. Okay, if it is a circle, it will be something like that, and your thumb will be pointing out of the page. So it is also correct. So you can use both ways. So for the Biot-Savart law, you use ds. This one is actually ds cross our head. You can also see B is pointing out of the page. If you use the right hand rule, following the direction of the current, and then your thumb will pointing out of the page. Okay, so this is the Biot-Savart law. We try to integrate it, so you plug this one into here. So mu0I over 4 pi constant. R square are also constant because this is a circle, or this is an arc. So the R to be a constant, capital R. So capital R square is a constant. We can also put it out. Yeah, so the remaining things, sine of theta is also theta always to be 90 degree. Okay, because this ds is a tangent line to the arc. Okay, this is a radius, so they are always perpendicular to each other. So theta always equals to 90 degrees. Sine of theta always equal to 1. So the remaining thing is integration of 0 to 5 ds. We need a bit change of variable. This is not that correct because this is ds. This is not that correct, but actually we need to do some change of variable. ds to be r times d phi prime. Okay, d phi prime. Okay. So after changing the variable, it should be correct, like 0 to phi d r times d phi prime. So r is a constant. We can also put this out. So it turns out to be r times phi. Nothing special. R times phi. So this r and this r square will be partly cancelled to be r. And then we also have a phi here. So it turns out to be like this. Okay, not that easy to remember, but yeah, anyway. So that is a special case for this equation. Is a center of a full circle, which means that here phi to be 2 pi, to be a full circle, 360 degrees. So if phi to be 2 pi, 2 pi and 4 pi will be partly cancelled to be a 2. So we have a mu0I over 2r. So this one is similar to the one except a pi, but they are two different cases. For this one, B equals mu0I over 2 pi r is for the long straight wire. For this one, it is for a circular eye. And then we consider the B field at the center point, which is a mu0I over 2r without the pi in the denominator. Okay, so here let's take a look at a sample problem. So it says the wire carries a current I and consists of a circular arc of radius r, and the central angle is pi over 2, 90 degrees. The two straight sections whose extension intersect the center of the C of the arc. What magnitude field B does the current produce as C? C is the center of this arc, and this wire, the extent to cross this C, also this one. Okay, so yeah, so let's see. For this one, ds is pointing to this direction, and then the r-axis also points to the same direction, which means that for db1, dB1 will be mu 0 over 4 pi and then times I ds sine of theta over r square. Okay, so this is a Biot-Savart law for the part 1. Okay, for the part 1. So I denote it as dB1. This one will be 0 because sine of theta is the angle between ds and r hat. R hat also points to the same direction. So this theta is 0 degree or 0 radian. Okay, so this is nothing but 0. Similarly, for the dB3, for dB3 also equals to 0. I mean dB2. Okay, dB2 is this part. For this case, theta equals to 180 degree, but sine of 180 degrees is also 0. Okay, so the only remaining part is this one. It's only this one. So okay, so B1 equals B2 to be 0, and the only thing is B3. B3 we can just use this 29.9. So this is nothing but mu 0 I phi over 4 pi r. Okay, so mu is 4 pi times 10 to negative 7. So mu over 4 pi is 10 to negative 7. And then times, okay, so we can just parenthesis it. So this whole thing is 10 to negative 7. And then times what is I? Okay, and I think no, there is no variable provided, so I just keep all the symbol. Okay, so this is mu 0 and then times I, and then phi is pi over 2, so make it pi over 2 and then 4 pi r. Okay, so let's do some cancellation. Pi and pi can be cancelled, so it turns out to be mu 0 I over 8r. Okay, so this is the answer to this one. And then when we need to consider the direction, actually we can use two ways. You can use the Biot-Savart law. For the Biot-Savart law, you can see ds is pointing to this direction, r is pointing to this direction. Okay, so r hat point to this direction. So ds cross r pointing into the page. So you can see that ds cross r is pointing into the page. And then using another way is to use your thumb follow the direction of the current. Using the thumb follow the direction of the current, and then your forefinger. Okay, so yeah, so at this point the eye is pointing to the right side. Okay, and then your forefinger will be something like that. So if your finger goes to this way, okay, so from here to here, so your finger will be pointing into the page. So it also tells you that yes, your forefingers will tell you that B3 will be pointing into the page, and as much as the B1, B2 are 0, so B is B1 plus B2 plus B3, so it is nothing but B3, which is mu 0 over 8r. Okay. Yeah, so